Hey there, welcome to another episode of Chemistry to Go. We're going to talk about electrochemistry today. It is taking redox reactions to work. So, please join me. Okay, we need to do a little review on redox reactions. So you need to remember that in redox, it stands for reduction and oxidation. And what happens is electrons are transferred. So a little easy way to remember it, if you recall the joke from last time, is that Leo stands for L, lose, E, electrons, O, oxidation. So lose electrons, oxidation. Leo goes GR. So GR is G, gain, E, electrons, R, reduction. So gain electrons, reduction. Just keep that in mind. Oxidation always involves the loss of electrons, and reduction always involves the gain of electrons. So we're going to get into what are known as electrochemical cells. They're made of two half cells. One half cell involves a half reaction, so either a reduction or an oxidation. And then the complementing other half cell is the other oxidation or reduction, depending on which one you've ever had. It's based upon two half reactions, and we need to understand that where there's a reduction, there's always an oxidation, and vice versa. And in an electrochemical cell, it means that we will actually put to work those traveling electrons, because the electrons will travel between the two half cells, and if we can separate those half cells, we can actually make those electrons do some work. After all, flowing electrons are otherwise known as electricity. We'll go over two types of cells. One is a galvanic cell, which is also known as a voltaic cell. Luigi Galvani and Alessandro Volta were two Italian gentlemen who spent their lives working on electrochemical cells. The idea behind either galvanic or voltaic cells is that they convert chemical energy into electrical energy. They are otherwise known as spontaneous cells. Spontaneous means that the reaction will occur. It doesn't make any reference to how fast it will occur or how slowly it will occur. It just says it will happen. The opposite of a galvanic or voltaic cell is an electrolytic cell. An electrolytic cell converts electrical energy into chemical energy, just the opposite of a galvanic. It is therefore classified as non-spontaneous, which means we have to supply energy to this reaction to enable it to work. So a non-spontaneous cell, again, makes no reference to time. It doesn't matter how long you give it, it's still not going to happen on its own. You have to supply some energy to it. What we're going to spend several slides worth doing is making a galvanic cell. So on this slide I ask you to write the reaction for solid magnesium placed in a copper 2 sulfate solution. You have Mg solid plus CuSO4 aqueous. It's a single replacement reaction, as you should well recognize, that makes magnesium sulfate that's aqueous and copper metal that is solid. Now what we can do is balance this reaction using the half reaction method so that we can see how it sets up its individual half cells. When I do so, I need to assign my oxidation numbers to every element in the reaction. So as I go from left to right, just follow me through it. I have magnesium in its natural state that has an oxidation number of 0. Copper in its monatomic ion state with a charge of 2 positive will have an oxidation number of positive 2. The sulfur will have an oxidation number of positive 6 because the oxygen has an oxidation number of negative 2. The magnesium ion on the right side is a monatomic ion with a charge of 2 positive, so its oxidation number is positive 2. The sulfur again is positive 6 and the oxygen negative 2. And the copper on the right side is 0. So as you look at that, you should be able to discern what is oxidized and what is reduced. And as we've done in the past, we will probably end up writing the half reactions, depending upon what order you want to put them. I've put the oxidation first. So magnesium goes from 0 up to +2 on the right side. So when I write my half reaction, I have magnesium yielding magnesium ion with a 2+ charge. The magnesiums are balanced. There's no hydrogen or oxygen to worry about. So we just have to balance it electrically. So I added 2 electrons on the right side. Again, this is oxidation, so it is losing electrons. In the reduction reaction, a copper 2 positive ion is becoming copper metal. So I bring down Cu2 positive, yields Cu. My coppers are balanced. I have no hydrogens or oxygens to worry about, so I just need to balance it electrically. And I'll end up adding 2 electrons to the left side to get the sides to balance out. When I normalize my electrons, the least common multiple of 2 and 2 is 2. So I need to multiply each half reaction by 1. I then distribute and add, and I end up with an overall reaction of Mg plus Cu2 positive plus 2 electrons yields Mg2 positive plus Cu plus 2 electrons. When I cancel my 2 electrons and put my spectators back in, I end up with Mg plus CuSO4 yields MgSO4 plus Cu. Notice it was already balanced before I started working with it. But the gist of this is to set up a galvanic cell that we can illustrate easily. So when you look on the slide that has the illustration of these 2 half cells in their separated beakers, notice you have one half reaction in one beaker and the other half reaction in the other beaker. They are connected by a piece of wire. Typically that wire is copper because it's such a good conductor of electricity. And because each half reaction has a solid component to it, meaning it's either a reactant or a product, I can make the electrodes, the substances that actually help to conduct the electricity, those particular metals. So what you see illustrated on this slide is that I have magnesium in the left beaker as an anode, that is an electrode that conducts electricity. And I have a copper cathode, that is another electrode that conducts electricity, in the right-hand beaker. I happen to have solid magnesium in the left-hand beaker that is willing to give away 2 electrons. Notice it sends them from the left to the right in this particular illustration, and will then become Mg2 positive. Notice in the right-hand beaker, I have Cu2 positive ions that are willing to accept 2 electrons from the other beaker. In doing so, they will deposit solid copper onto the cathode. The sulfate ions no longer are needed by the copper as it becomes solid copper, so they need to go somewhere. And that's the point of the salt bridge. You see the piece of tubing that connects the 2 beakers. It has sodium and chloride ions in it because it needs to have an electrolytic paste or something that can conduct ions through it. In this particular case, sulfate ions will flow from the right beaker, where they were attached to the cupric ion, into the left beaker, where they will essentially hook up with the magnesium ion. As this reaction progresses, the blue color of the copper ion will fade, and the magnesium solution will form magnesium ion and sulfate ion, which are colorless. We would notice a degradation in the magnesium electrode and a building up of copper metal on the copper cathode. So let's talk about the components of this galvanic cell. You had an anode, which is the electrode in a galvanic cell at which oxidation takes place. Again, the electrode at which oxidation takes place, where electrons are lost. You had a cathode, which is the electrode at which reduction takes place. The electrode where electrons are gained. If you take a look at that illustration again, it should make sense. But to complete the circuit, we have to have what's known as a salt bridge. The salt bridge's job is to allow for the flow of ions. The wire's job is to allow for the flow of electrons. So we have electrons flowing and we have ions flowing, and in doing so, we make a complete circuit. That flow of electrons is called electricity, and it's measured by its potential to flow. Its potential to flow can be measured as either a half cell potential or a complete cell potential. And it's defined as the pull on the electrons. It is not a push, rather it is a pull on the electrons. It is also known as the electromotive force, or EMF, measured in volts, represented with an uppercase V, and a volt is in actuality a joule, which is a unit of energy, per coulomb, which is a unit of electrical charge, represented as uppercase J per uppercase C. We can use measurement devices to determine the voltage output of a galvanic cell. They're called voltmeters for obvious reasons, or potentiometers, and I'll explain each. A voltmeter can be classified as analog or digital. An analog voltmeter you may have seen with two lines coming off of it, typically a red cord and a black cord, indicating positive and negative terminals, respectively. And it has a needle, rather like a speedometer needle, that moves in response to the amount of voltage it is allowing to pass through it. It actually has a little bit of error built into it because there's a certain amount of resistance that is associated with moving that needle. So a digital voltmeter is actually one that is preferred in that there's less resistance required to put out a typically liquid crystal diode measurement of the voltage. Same kind of concept, but just using less resistance. A potentiometer works a little differently in that it sets a voltage at 0 as a reference point and then measures other voltages with respect to that reference point, which means it's all relative to whatever you've set as the reference point. If a half cell or a whole cell has positive cell potential or half cell potential, it's known as a spontaneous cell. If it has negative cell potential, it's known as a non-spontaneous cell. What you'll get in my class is known as a standard reduction potentials chart. If you're not in my class, you may certainly look this up on the internet. They are very easily found. In a standard reduction potentials chart, you only have reduction reactions, which means electrons are always on the left side because they're always gained. So if you're looking up an oxidation half reaction, you won't find it. You have to look up the reverse of the oxidation, flip the sign of the cell potential that you find to be able to use it. And just as we add half reactions to get a whole reaction, we will add standard half cell potentials to get the standard cell potential. Standard means that it's been recorded at 1 molar concentration, 1 atmosphere of pressure, and 25 degrees Celsius. A little misnomer there because we think of standard temperature as 0 degrees Celsius, but in laboratory conditions, standard is 25 degrees Celsius. So if we go back to that same reaction we were working with, where magnesium was oxidized to form magnesium ion, and copper, 2 positive ion, was reduced to form solid copper. And you look on your reduction potential sheet or online reduction potentials, you will not find the reaction of Mg yields Mg2 positive plus 2 electrons. Rather, you will find the reverse of it. When you find the reverse of it, you need to recognize that that is the reduction reaction, and we are dealing with the oxidation reaction. So you flip the sign of the voltage that you found, and you should find that the potential of that oxidation reaction under standard conditions is positive 2.37 volts. When you look up the reduction potential of Cu2 positive plus 2 electrons yields Cu, you do find it. And the standard reduction potential is positive 0.342 volts. I add my half reactions to get my balanced equation that I had previously obtained, and I add my reduction and oxidation potentials. I will never, by the way, multiply those potentials by the multiplier outside of the parentheses. Notice that my parentheses stop at the end of the half reactions. They do not extend over to the potentials. So that when I add positive 2.37 volts and positive 0.342 volts, I get a standard cell potential of that particular reaction to be positive 2.7 volts. Which means if I were to set up a voltmeter in the midst of those two beakers that you previously saw, it should give me a reading of 2.71 volts. I want to briefly go over what's known as writing a line notation. In writing a line notation, it is standard practice to separate your oxidation and reduction reactions with parallel lines, two parallel lines. Those parallel lines represent the salt bridge. I then separate reactants from products or products from reactants using a single line that is vertical. My oxidation reaction is written on the left side of the salt bridge. My reduction reaction is written on the right side of the salt bridge. If I have solids present, they are the outermost, whether left or right side, substances. So you see I have a generic reaction written there that is X solid yields X positive aqueous, separated by a salt bridge. Y positive aqueous yields Y solid. When I apply that to the reaction we have been working with, I have Mg solid yields Mg2 positive aqueous, separated by a salt bridge. Cu2 positive aqueous yields Cu solid. From that line notation, I should be able to discern that I have my oxidation reaction on the left, so Mg yields Mg2 positive, and my reduction reaction on the right, so Cu2 positive yields Cu, and be able to write my half reactions. And you notice that I've done so, and I get my overall reaction that I've had. I've given you a line notation of Cu solid yields Cu2 positive aqueous, separated by a salt bridge where Ag1 positive aqueous yields Ag solid. Now I expect you to be able to write your half reactions from that. You may turn the PowerPoint or podcast off at this point and write it and then come back. And as you come back, you should see that you have Cu yields Cu2 positive plus 2 electrons, and Ag1 positive plus 1 electron yields Ag. When I look up the potentials of each of those half reactions, I notice that I have Cu's oxidation potential, once I flip its sign, is negative 0.342 volts. Ag's reduction potential is positive 0.8 volts. Notice to normalize my electrons, I need to multiply the reduction reaction by 2, but I do not touch its reduction potential. It is not multiplied by 2. I then add my half reactions and my half cell potentials and get a balanced equation, once I cross out my electrons, of Cu solid plus Ag1 positive, 2 moles of it, yields Cu2 positive plus 2 moles of Ag solid. The standard cell potential is positive 0.458 volts. Let's move on now to a more practical application of electrochemical cells, and that is discussing batteries. A battery is truly defined as a series of electrochemical cells that are connected to each other. When I have batteries, I will complete a circuit. That's the idea of having a battery in place in a device. It completes the circuit being the electrical flow. So if you have, for example, a flashlight, the electricity is waiting to flow. It only happens when I put the battery or batteries in to the flashlight and connect the current, essentially, by completing it. I'm going to go over two classes of batteries, dry cell batteries and wet cell batteries. Dry cell batteries are exemplified by a flashlight battery or a watch battery. Many other examples, but those are two common examples. A wet cell battery is exemplified by a car battery. Again, other examples, but that's a typical example. So in an example of a dry cell battery, we have a carbon zinc battery. It's a typical, say, AA battery. It consists of a zinc casing, which serves as the anode, the electrode where oxidation takes place. A carbon rod, which serves as the cathode, that is the electrode where reduction takes place. Manganese 4 oxide, it's a black solid substance. It's actually what is reduced in the carbon zinc battery. The zinc is actually oxidized. And you've heard of alkaline batteries. Alkaline batteries will substitute potassium hydroxide rather than ammonium chloride in their electrolytic paste, which is what their salt bridge is. You see on this slide a cutaway schematic of a carbon zinc battery with the carbon cathode that's surrounded by the black manganese 4 carbon paste. You have the casing that is zinc, typically surrounded by a little bit of paper to advertise the battery. You have an electrolytic paste, which is considered dry, that is ammonium chloride and zinc chloride. And then you have a little paper spacer that enables the ions to flow. So, the reactions at hand, the half reactions rather, are zinc becomes zinc 2 positive plus 2 electrons, and 2 moles of ammonium ion react with 2 moles of manganese 4 oxide and 2 electrons to yield manganese 3 oxide solid, 2 moles of ammonia, and water. And we'll work on calculating the potentials of that a little bit later and getting the actual voltage associated with it. Let's look at a wet cell battery, classically exemplified by a lead acid storage battery. In this reaction, you have solid lead reacting with solid lead 4 oxide and sulfuric acid in a reversible reaction to make lead 2 sulfate that's solid and water. It is both a spontaneous and non-spontaneous cell. As you can see in the schematic that I've provided for you, you have lead plates and lead 4 oxide plates. A typical car battery consists of 6 of these cells. Those cells are connected to each other with their cell connector that you see at the top of the schematic. The electrolyte is the sulfuric acid. Most car batteries that you encounter these days are not able to be opened. They're called sealed batteries, which means they don't need to be maintained. When I was growing up, you had unsealed batteries, and you actually would check the specific gravity of the sulfuric acid and adjust it as needed to keep the battery working. Now I say that it's spontaneous and non-spontaneous because when you start your car, you're converting the chemical energy in the battery into electrical energy that is sent to the starter that will actually end up starting the engine. Once your car is running, you have an alternator, or some older cars might have generators that convert the electrical energy back into chemical energy. And what that actually means is the battery is recharged as you drive it. So a little common sense tip here is that if you ever have to jump start your car because your battery is dead, don't jump start it and then turn it off. Jump start it, drive it around, and as you drive it around, you end up charging the battery, perhaps, and rejuvenating it. One of the final things we're going to look at is the concept of concentration cells. As I said, we've been looking at standard cell potentials, those that are 1 molar, 1 atmosphere of pressure, and 25 degrees Celsius. Well, if I change the concentration from 1 molar, then I have to do a little tweaking of my calculations. It means that I need to do additional calculations. And that enables me to actually manipulate the cell potential to get a particular voltage that I desire. Meaning, I think you notice that some batteries are 12 volts, some are 9 volts, some are 1.5 volts. Well, it's not magic that enables us to get those particular voltages. It's tweaking the concentrations that enables us to get those particular voltages. So we use what's known as the Nernst equation. It's a funny little name, isn't it? I believe he was a German gentleman. And the Nernst equation tells us we can calculate the cell potential, notice no standard or little degree sign, by taking the standard cell potential, subtracting from that 0.0592 divided by n multiplied by the log of Q. Pay close attention to the parentheses and the braces. N represents the number of normalized electrons, or the number of electrons that you have canceled from your half reactions. Q represents K, or equilibrium constant, under initial conditions. That means products, concentrations raised to the power of their coefficients, divided by reactant concentrations raised to the power of their coefficients. So let's take a look at our fun little reaction where we have 0.5 molar solution of copper 2 sulfate reacting with magnesium metal. A 0.75 molar solution of magnesium sulfate is one of the products. What is the cell potential is my question. The first step is to write the two half reactions. Well, you've already done that. We'll then write the balanced equation. You've already done that. We will determine N. You've already done that because you've crossed out your number of electrons. We'll determine the E standard of the cell. We have already done that. And then we will use the Nernst equation to solve for E cell. And that is the only new part to this particular reaction. So you see we've gone through sequentially what we needed to do to get us to this point. So I've given you the line notation, which enables you to get your two half reactions with your standard half cell potentials. To get your overall balanced equation, notice you are normalizing by crossing out 2 electrons from each side, and your E standard is positive 2.71 volts. When I plug into the Nernst equation, I plug in E cell equals 2.71 volts minus parentheses 0.0592 divided by 2 because I crossed out 2 electrons. Close parentheses times open parentheses the log of open parentheses again 0.75 to the first divided by 0.5 to the first, close parentheses twice, and close my braces. Notice my concentrations are just raised to the first power because all of my coefficients were 1. So I made this one pretty simple. When I end up doing my math, I should get an E cell under those non-standard concentrations to be 2.70 volts. So that means I lowered the voltage a little bit by, in this particular case, lowering their concentrations. Alrighty, and a final thing to leave you with here is that you have a line notation reading Cu solid yields Cu2 positive with a concentration of 0.01 molar, separated by a salt bridge where Ag1 positive with a concentration of 0.025 molar yields Ag solid. You need to write your two half reactions, determine your voltages under standard conditions, normalize your electrons, get your summation in your net ionic equation, get your E standard for the whole cell, plug into the Nernst equation, and you will get your voltage under non-standard conditions. Okay, I don't have a terribly witty joke for you this time, but what do you think Volta said to Galvani when they got into, I don't know, a tea afternoon? What do you think? He said, "Oh, Luigi, this is electrifying tea." Get a tickle out of it. Okay, we don't have too many more of these for this year, so you enjoy this. Hope you had fun with it. You take care. Bye.